Jason Thompson is Vice President of Product Development and Engineering for Cloyes Gear and Products, Inc., based in Fort Smith, Arkansas. Cloyes is the North American leader and global designer, developer, manufacturer, and distributor of timing drive systems and components for the automotive aftermarket and original equipment manufacturers. Jason directs all engineering departments for Cloyes across timing components, including the all-new VVT components and water pumps. He brings more than 13 years of aftermarket automotive design experience to system design. Jason earned his Bachelor of Science in Mechanical Engineering from the University of Arkansas. Cody Smith serves as Technical Support Manager for Cloyes and manages all technical customer interaction, including the production of a successful line of instructional videos with more than 2.5 million views. He is also a key member of the product development team, overseeing the development of new product lines, including water pumps and VVT components. Cody brings more than 15 years of automotive parts industry experience to Cloyes and is an avid automotive hobbyist with success in both autocross and dirt track racing. He earned an AA degree from the University of Arkansas, Fort Smith. Today, Jason and Cody will discuss the technologies involved in each part type that is included in a timing drive system, along with the different drive systems commonly used. They will also cover some of the new exciting products that Cloyes has recently launched. Before I turn this over to Jason and Cody, please remember that if you have any questions, you need to type them into the question box, and we'll have Jason and Cody answer them at the end of the presentation. Now here's Jason Thompson and Cody Smith of Cloyes Gear and Products.
There we go. Thank you, Joe. And thanks to the association for this opportunity. Appreciate everybody that's taking the time to listen in today, and we'll watch the recording later. I'm Jason Thompson, and today Cody Smith and I will present timing drive system technologies. Our agenda will cover category drivers, technical information, product expansion, R&D and quality control, and finally, training information. First, I'd like to cover a brief history about Cloyes. We're almost 100 years old, founded by Raymond T. Cloyes in Cleveland, Ohio in 1921. Acquired by Harry D. Myers in 1953, and that Myers family held on to Cloyes for 3 generations. Throughout the 70s, 80s, 90s, and early 2000s, Cloyes acquired some timing-related companies. Leading up to 2004, Cloyes established distribution in Aguascalientes, Mexico. By 2006, the Cloyes company went from family-owned to the world of private equity. Leading up to current 2018, we were acquired by Hidden Harbor Capital Partners. I can start with the Fort Smith Distribution Center, servicing more than 300 customers, over 600 locations in the U.S., Canada, and abroad. Delivery order fill rates of 95% or greater, with the order turnaround in 48 hours or less. Within this facility, we have sales, customer service, electronic cataloging, engineering, product department, development, sourcing, procurement, accounting, and distribution. Very similar, our Aguascalientes, Mexico distribution center houses the same departments, servicing roughly 100 customers in Mexico, Central America, South America, Europe, and Asia Pacific. In 2019, we increased the capacity of this facility by 20% through investment and improvement in material flow. Very excited to talk about our Paris manufacturing facility. We maintained ownership of the Paris, Arkansas manufacturing facility. The employee skill set is a group of machinists with 20, 30 plus years of experience, highly skilled group of folks. Manufacturing components, including gears, sprockets, automotive original equipment components, aftermarket, and high performance. We're very, very proud of our billet high performance components coming out of this facility and that we match in this distribution center in Fort Smith. Key processes in this facility that they specialize in: machining, hobbing, shaping, heat treatment, everything it takes to get a part to its final form. The quality department in that facility not only supports manufacturing, but also supports engineering out of the Fort Smith location. I'd like to show some industry information. This is the age mix of vehicles as applied to aftermarket. What this is essentially showing is that vehicles 8 years and older account for almost 60% of the vehicles as of 2019 on the road. Most importantly, vehicles that are 12 years and older are increasing by 4%. This is really good for the aftermarket. Vehicles in operation hit 272 million by 2018, forecasted to be up 8% by 2023. This is showing the VIO history from 2002 through that forecasted 2023. A little evolution to timing drive systems. Starting out as gear drives, moving to 3-piece timing chain sets with 4-cylinder small displacement engines coming on in the 90s. Well, further back than that, but at their high point in the 90s, timing belt systems. And then moving to multi-piece, more complex timing chain systems that include variable valve timing. I will say that these designs historically were in tandem, and all of these are still on the road. So to speak a little to that trend, window from 1980 through 2023, and as of 1983, 90% of the systems on the road were chain systems. Because of small displacement 4-cylinder timing belt systems, by 97, chains were down to 31%. 2016, back up to 91%, and projected to be at 83% by 2023 with a mix of belt and some electric vehicles. Next slide will actually pop in our sweet spot. So we're trending upward. Our sweet spot is roughly 8 to 12 year window, or 8 to 12 year old vehicles, and we are trending upward. So I'd like to talk a little bit about the evolution of chain systems themselves and their complexity over time. What's the perfect example is a Chevy Cavalier from 2001 to 2002. 2001 was a older architecture push rod engine with a 3-piece set and a tensioner. About 2002, they developed the Ecotech platform, moving to a double overhead cam architecture. That made it go from 4-piece timing set to 11-piece timing set. It's not an overly complicated system. It's just what is required for an overhead cam system. And then eventually they added variable valve timing system to this application. Another interesting example is the Explorer engine, the Ford 4.0, which was a push rod V6, and then moved to that same architecture, moved to a single overhead cam designed with stock motor. And due to them using the same block and adapting overhead cam technology, it's extremely complex, as everyone in this industry knows, prone to failure as well. It had a primary system, a front and rear cassette, moving this application from 5 components to 16 components, extremely complex. And now I'll move it over to Cody to describe different engine types.
Thank you, Jason, and good morning, everybody. When we're talking about timing chain systems, we're talking about the components that connect the camshaft or camshafts to the crankshaft and keep those shafts in time with one another. These systems obviously vary greatly depending on the engine at hand. In overhead valve or push rod engines, the timing system usually consists of a cam sprocket, a crank sprocket, and a chain. And the use of a tensioner is also common on later model engines, like you see on the picture on the left here. It's a Gen 4 GM engine that utilizes a tensioner. Like Jason touched on a little bit, 70 years ago, it was common to see a gear-to-gear type timing system in these overhead valve engines, but today it's almost exclusively chain. Most modern engines, as you all well know, are of the single overhead cam or double overhead cam arrangements, and this is where the complexity of modern timing systems come into play, including the introduction of variable valve timing. So because of the long distance between the crankshaft and the camshafts of overhead cam engines, multiple piece timing systems are required to tension the system and route the timing chains effectively. Now, on top of the multi-piece primary systems, dual overhead cam engines typically have secondary timing systems that connect the camshafts of a particular head. So you'll have a primary chain that runs from the crank up to the cam sprockets, the primary cam sprockets, and then you'll typically have a secondary sprockets on each camshaft of a head, which are connected by a chain and typically a tensioner of some kind. What is variable valve timing? I mentioned it briefly on the last slide. Variable valve timing or variable camshaft timing is commonly referred to as VVT or VCT, respectively. VVT is the technology that allows a camshaft to be advanced or retarded relative to crankshaft position variably across an engine's RPM range. So this is done by utilizing a two-piece sprocket that's called either a phaser or an actuator, as opposed to a one-piece sprocket that are used in traditional engines. Using the engine's oil pressure through oil porting, and it's controlled by a solenoid and the engine's management system, each phaser can advance or retard cam timing on one or multiple camshafts depending on the arrangement. So this porting could go through, like on the Ford modular engines, it'll go through the camshaft, journals. So, journal wear in that situation is very important. This technology allows manufacturers to tune engines for both fuel economy and emission requirements while maintaining or even increasing engine horsepower and torque output. This is almost the sole reason why we can have 400 horsepower engines that still get 20 miles to the gallon. So it's good technology. But of course, with the increased complexity comes a higher potential for misdiagnosis of timing system issues. So like I touched on, a lack of feed to the phasers due to worn cam journals, maybe poor oiling system health, clogged oil passages, or component failures can cause VVT system instability, resulting in timing system instability. I'm going to move on to timing chains. There are two main designs of chains found in automotive applications, roller and inverted tooth. Roller chains, the first we're going to touch on, they use a roller in between links to engage with sprocket teeth to eliminate drag. They can be identified by a few key dimensions, the first being pitch. Chain pitch is the measurement of the center of one pin to the center of the next pin. So typical pitches for automotive roller chains are 3/8 of an inch, a 1/2 inch, and then on the metric side, 7 millimeter and 8 millimeter are both really common. The second dimension is number of links. The number of links, you can obtain that by counting the links around the chain, but you got to be sure to include the inner links for that total link count, or you can just count the outer links and multiply that by 2. And that'll give you your total number of links of a chain. And then the third dimension is going to be your roller diameter size. So typical roller diameter sizes for automotive chains going to be like 1/4 inch, 250 thousandths, 335 thousandths, and then both 4 millimeter and 5.65 millimeter as well. The other design of chain used in automotive application is inverted tooth chain, or some of you may know it as a silent chain or link belt chain. And these chains are made by simply lacing a series of links connected by pins. This inverted tooth design has been proven to be a durable option implemented by manufacturers to reduce noise and vibrations. And this is done by utilizing profile engagement between the chain and sprocket. And Jason is going to touch on that here in just a little bit. In inverted tooth chains, pitch and number of links are found using the same process as I just went over on the roller chains. You'll find that most late model chains have marked chain links that align to the sprocket timing marks for installation processes. So on that top picture on this slide, you'll see a bright yellow mark and then two darker, almost black marks. So those are used for, timing system installation and getting the engine in properly in time. Now, like I said, Jason's going to dive a little further into timing chains.
Thanks, Cody. Chains may seem simple, but there's actually a lot of detail with chains. Roller chains are assemblies of inner links, outer links, rollers, bushings, and pins. Inverted tooth chains are assemblies of links, inner, outer, and pins. Each of these components have its own unique material and heat treat requirements. This is to meet ductility and wear properties for long term. For example, components that are too hard, they would brittle fail. We know this from analysis. Components that are too soft are going to stretch and wear prematurely. There's a delicate balance of material and heat treatments, and this is coupled with a series of slip and interference fitments between these components during the assembly process. It's extremely important that during this assembly process that you accurately repeat these tedious fitments in a high production environment, and then the whole system is riveted together to hold everything together in the end. In tandem with the assembly process and everything just discussed, all chains go through a pre-stress. Pre-stress is very, very critical to chain fatigue life. The chain, what's unique about this situation is that you must assemble a chain in such a fashion that you're able to pre-stress it to a load requirement, and in the end still meet length specification. Widely varies between chain specification from 6.35 millimeter small pitch chain all the way through half-inch pitch roller chain, but roughly 25 to 45% range of pre-stress of that unique chain's ultimate breaking strength is applied. A couple of things I like to cover just in the detail here. If you look at the upper right figure, it is showing a pin, metallurgical analysis of a pin microstructure. And this is really speaking to what it takes to build a pin so that you have the right amount of ductility, but then good wear properties. So this is actually showing a chromized layer where the pin is heat treated so that it's somewhat ductile, but then has a very hard surface for these slip and interference fitments for wear over time. Another process to achieve the same goal with a pin is carbonitriding, and that's to the top left. And then the bottom right, you'll see yet another process, carburizing. The carburizing is more of a gradient into the pin, less of a hard line layer. But all these processes create a pin that is ductile enough so it does not fracture, yet has very good wear properties between the components. I'd like to point out something. The bottom left is actually showing some micro cracks on a link. This is an example of a chain that we were doing analysis on, and it failed analysis because of it was heat treated and it was too hard, and it actually had micro cracks just from the assembly process itself. So this is all the stuff that we're looking out for when we're developing chains, so that we're producing chains that are going to last in the field, both fatigue life and ultimate breaking strength. I move on to the more dimensional side, key feature, which is link design. Roller chains have a simple roller to tooth engagement. It's still critical that, like Cody said earlier, you're decreasing the amount of drag and then engagement, disengagement. And there is some tooth profile detail to the sprocket side so that this roller rolls in and rolls out very smoothly. But it's simpler out of the two between roller and inverted tooth. One thing that roller does introduce to the system is a certain amount of noise or vibration because of this engagement, disengagement of the roller into that tooth profile. Because of that, you'll see some manufacturers, across use a cushion ring concept. This is GM through Toyota. We use cushion ring concept to decrease this noise on roller systems, engagement, disengagement noise. Inverted tooth chains reduce noise by engagement design. This wildly varies from OE manufacturer, whether it's Nissan, Toyota, Honda, or Ford, GM. There's a lot of concepts and a lot of these design behind this engagement. It's an involute to involute engagement or profile to profile engagement between the inner link of the inverted tooth chain and the sprocket tooth form. What's most important in the aftermarket is to acknowledge these design differences and these intentions. And if you deviate from it, you do it intentionally because you want to change something about the design, or you need to be very careful to maintain that design. I'd like to take this opportunity to show these diagrams or describe these diagrams a little bit. So these are actual CMM link raw data overlaid onto drafted tooth forms, both of these. So the white dots are actually CMM scans of inner links, and the yellow lines are drafted tooth forms. If you look at the one on the right, you will see a design in which the link is making contact with the teeth on either side. If you look to the left, you'll see a link that is making contact with the tooth at the center. Entirely two different concepts. So this is the kind of detail that I'm talking about when it comes to link design and the profile to profile engagement to reduce noise in these systems. This leads into what happens to a chain. How does it fail? What's the life cycle of a chain? So I'm going to cover the two main categories. The two ways that chains fail are either fatigue or ultimate failure. Ultimate failure occurs when the chain has met its ultimate breaking strength by an outside catastrophic mechanical force. In this industry, we all know, a thrown rod or a valve seat that dislocates, or any other mechanical failure where the system was turning and very quickly stops turning, produces enormous shock loads, and ultimately will fail a timing chain and just looking at the engine as a whole. Fatigue failure occurs when the chain has met its max number of cycles at a given cyclic load and stretches beyond system stability. You're going to hear this common theme about system stability or instability as we go through each component type, and then button it up with the slide on the system itself. So this will all come together as we get to these slides. What we find is that it's a combination of the two. It's really one or the other, but you have a combination of the two that leads to failure. If a chain fatigues beyond system stability and the driver or operator of the vehicle is not given some type of notice, either a check engine light or an audible rattle, or they just don't notice, the chain begins to whip. At that point, it is not stable, and the chain is too long, and the system can't maintain stability, and the chain begins to whip. This whipping effect aggressively accelerates the fatigue failure, or decreases its fatigue life. So if this is not caught in time, it will ultimately fail. But it's a fatigue failure leading up to an ultimate failure. Other things that can create accelerated fatigue failure are things like engine misfire or VVT system malfunction. It creates shock loads, harmonics within the system, and it accelerates that fatigue life up to a point of either notification, check engine light, or audible rattle, or leading to an ultimate failure. Now I'll hand it back over to Cody to give a general description of our Sprocket technologies.
Yeah, so sprockets in automotive applications, you're going to find them made of billet steel, cast or ductile iron. We also use forgings and centered middle sprockets as well. In modern complex engines, you're going to find sprockets commonly driving more than just the camshafts and the crankshaft. Sprockets can be found driving water pumps, balance shafts, and oil pumps. The sprocket, the teeth on a sprocket, they must be designed to work with the specific chain designs, roller, bushing diameters, and the pitch of the chain. And you'll also find timing marks commonly found on the sprockets for installation purposes. Sprockets typically feature some kind of a dowel hole or slot, a keyway, or an indexing feature of some kind to ensure proper shaft engagement for proper shaft timing. This is a very important note. Sprocket indexing features are not designed to withstand torque loads from the timing system. They're only there to properly set shaft timing until the sprocket is attached by its respective bolt or bolts. The clamp load of the attachment bolts is what holds the sprocket in place. So if you ever experience like an indexing feature failure, it's not going to be the sprocket's fault. You know, those indexing features are just simply not made to hold the sprocket in place. When you see a failure like that, it was because the clamp load of the attachment bolt was overcome. So back to Jason. Jason's going to dive into sprocket technologies.
So I'm going to cover sprocket design and wear together. It kind of goes hand in hand. As Cody covered, there's a wide range of materials used in sprockets, and each of these materials are very unique in specification and hardness requirements. How you manufacture, how you inspect, quality control is very unique to each material. Cloyes specializes in sprocket manufacturing and machining the products out of all these materials, all the way from billet through secondary operations on powdered metal, and there is a lot of detail there. Powdered metal is very unique in material, whether you're using an iron nickel or iron copper material, or by application you're selecting this material, and you're trying to achieve both density and hardness out of this powdered material. Because of this and how complex the pressing and the sintering process is, the material and achieving density, there are things that could go wrong, and I want to cover a couple of things that can go wrong so you understand what it is that we're looking for when developing powdered metal products. If you look at the top right, you'll see an example of a heat-treated tooth that has decarb on the surface. That's that kind of light band at the tip or that edge you see on that microstructure. And what that was from the heat treat furnace. It pulled the carbon out of the part as it was going through the heat treat, and so that was a heat treat furnace issue. If you look at the bottom right, you'll see a free copper in the microstructure. It looks like pennies in the microstructure. It really looks this way. This is reflective of a part that has been pressed and went through the sintering furnace, but the sintering furnace did not meet temperature, so the copper was not melted. And so these are all kind of details we're looking for when we're developing powdered metal technology, so that our production does not have these flaws. We're also looking out for cracks, of course, magnaflux the components, the powdered metal components, to make sure we don't have any cracks in our powdered metal components. Sprocket tooth form is most critical design feature, and just like with the chain links, and this is the chain link inner profile or roller engaging with the tooth profile of the sprocket. Extremely critical for decreasing noise and vibrations. You got to have smooth engagement and disengagement. The tooth form itself includes profile or involute, index, which is tooth to tooth accuracy, and lead, which is across the tooth, whether it has no angle or some angle, depending on sprocket or gear. If you look closely at the image there of that sprocket, that's actually showing an example of a worn sprocket. This was a modular crank sprocket, high mileage, heavily worn timing system. And this is an example of tooth wear. You can see that inverted tooth link pattern on the teeth, and you can actually start to see some pitting. So you're actually seeing the surface deteriorate, the heat-treated surface of that tooth form deteriorate over time with wear. That's typically what you're going to see with a sprocket, and sprockets usually make it to the end of the system cycle without failure. But if you going into a system, this helps you decide that you should or should not replace sprockets. If you're seeing that kind of wear on a sprocket, you should replace your sprockets along with all the other components. With all that being said, and no flaws in the part, sprockets typically don't fail. If there's a flaw, a material flaw or dimensional flaw, that could lead to a failure. But setting that aside, sprockets, good parts without flaw, is not going to fail unless there's an outside catastrophic mechanical force, engine's turning, and then engine is all of a sudden not turning. And that can break teeth along with breaking the chain and everything else in the system. Now we'll go back to Cody on tensioner types.
Yeah, chain tensioners, they can refer to hydraulic units backed by a mechanical spring or spring-only units in some applications. Automotive tensioners, they may have built-in chain contact surfaces, or they may utilize a separate pivoting tensioner guide to apply tension to the chain. Timing system tensioning is necessary to stabilize and absorb system harmonics during operation, and it also provides a range of operation to endure chain or belt fatigue life. So as a system gets older, the chain's naturally going to elongate or stretch, and tensioners are designed to, extend as far as it is necessary to keep that chain stable over time. It's important to note tensioners can have multiple features unique to a specific application, so it's important to research the application and follow installation instructions. These features may include internal or external ratcheting mechanisms that sometimes require a specific activation procedure after installation. These ratcheting mechanisms, what they do is they'll allow a tensioner to extend out as far as possible to provide tension to a chain over the life of the system, like I just mentioned, but they limit the inward movement to prevent system failure. So in cold start situations where a tensioner is primarily a hydraulically operated tensioner, that's going to have a mechanical spring, and it may have a ratcheting mechanism of some kind. So when the engine started up and it doesn't have full oil pressure available, the system or the tensioner has a means of keeping the chain tight until that oil pressure gets to it. So being hydraulically operated tensioners, a healthy oil pressure and quality is absolutely imperative for proper function. And you're back to Jason on tensioner design.
So tensioners are fairly complex hydraulic and mechanical units. They're multi-piece assemblies that include many specific materials and heat treatments. The materials include powdered metal, steel, nylon, rubber. The powdered metal components, of course, to a density, to a hardness. The steel components range from stamped sheet metal all the way through spring steel wire for the springs, billet, extruded wire for machine pieces, whether it be a bore or a piston, rubber for gaskets, and nylon for contact surfaces. So the nylon can go one of two ways. It's all going to be PA66, but if it's for a housing, it's going to be PA66 nylon with glass fiber reinforcement for structural integrity. If it's a contact area against the chain or a wear surface, it will just be 100% PA66. This material is very durable to wear over time and holds up well at temperature, at engine temperature. Tension is produced mechanically with the spring and hydraulically with oil pressure, and what's critical here is that in those moments or seconds when engine is in startup and you do not have oil pressure yet, then your mechanical features are stabilizing the system. So you have mechanical spring, ratchet mechanisms, all kinds of mechanical functions that are holding the system stable until oil pressure gets there. One thing I will add to it, though, is that a hydraulic check valve in the piston itself does maintain oil in the tensioner. So that does help during startup as well as keeping that tensioner from collapsing with hydraulic pre-charge. It's not positive pressure, but it's got a reservoir of hydraulic fill. Key to the hydraulic function is the piston to bore fitment. This is something that has to be very closely monitored during production because you're machining a bore and you're machining a piston, and they got to come together, and you've got to have a tolerance stack that's always within a very tight tolerance to have the correct piston to bore tolerance. If the piston to bore tolerance gets too large, then you'll have hydraulic failure due to hemorrhage.
And on that topic, Jason, there's something I wanted to mention on that last slide. On a tensioner like the one pictured here, it's important to torque the attachment bolts to the OE specification to avoid warpage to the tensioner housing. Just like you were just talking about, that tensioner piston to bore is a critical feature. And excessive torque on the attachment bolts can distort that the tensioner cylinder and cause some piston to bore friction. So that is another important feature there. Sorry to interrupt.
No, thanks for that, Cody. It's good. So with all that being said, most tensioners do include a check valve that is crucial for positive flow into the tensioner and control backflow. Now, this doesn't mean there's 100% backflow blockage. A lot of tensioners have some type of venting or backflow control, but the check valve is critical to that flow come into the tensioner and the dynamic backflow control. And like I said, setting overnight, it actually maintains a hydraulic feel to these tensioners. Tensioner gaskets are included as applicable, whether it's a sheet metal or soft metallic gasket or a rubber gasket that's included. So next, I'd like to get into tensioner functionality. Tensioner is designed to apply tension to the timing drive system as the chain system fatigues over time. So this is a consistent theme that, and I will back up too on this tensioner discussion. I'm focusing in on hydraulic tensioners because that is the majority of what we are dealing with at some point in time. There are a handful of mechanical spring back tensioners that we still have in applications, but for the purpose of covering technical detail, I'm focusing on hydraulic tensioners, which is the majority of the product. But anyway, tensioners are designed to apply tension to the timing drive system. It's something you're going to hear you continue to have heard over and over again as the chain and system fatigues over time. So chain fatigue is the primary driver to system fatigue. That is the chain stretching over time. Sure, sprockets are wearing a little bit, nylons are wearing a little bit, but the chain stretching over time is really the main driver to system fatigue life. So as a consistent theme, tensioners, they're applying tension to the system throughout this fatigue life. They're keeping up with that chain stretch over time. If you look over to the right, you will see a Ford 5.4 F-150 with 160,000 miles on it at the top right in that image, and see the amount of tensioner extrusion, how far the tensioner piston is coming out of the housing, pushing on that tensioner shoe. This tensioner was, 75, 80% at capacity, and we were doing real-world install of our new BVT units, and so it was an opportune time to go ahead and put a fresh timing system on it. The system had not failed yet. You look below, and you will see the new system and how little extrusion there is of the piston coming out of that housing, pushing out tensioner shoe. And this gives you a very good visual of what's happening over time, how the tensioner is keeping up and applying tension, keeping the system stable through system fatigue, chain fatigue. So I'm going to go through some things here. I've got the word can in quotes. Tensioners can wear between the piston and bore of the housing, increasing the piston to bore tolerance, resulting in decreased hydraulic pressure. That can happen. Check valves can become weak and allow a little bit more backflow than originally, maybe a little startup rattle or something of that nature. Tensioner gaskets can begin to leak between the mounting surface of the engine and the tensioner housing. But I really want to button this up. Those are all cans or possibilities. Even though those things are cans, what generally happens is the tensioner operates the duration of the chain fatigue life or the system fatigue life. That's generally what we see. You generally don't see a tensioner fail. We see a chain so long that it is beyond the tension capacity to keep tension on the system. A tensioner has a range of motion, and when it hits that max range of motion, it can no longer stabilize the system. At this point, tensioner's met its max extrusion due to chain stretch and system fatigue, and the system becomes unstable. Chain begins to whip. When you get into chain whip, as discussed on the chain slides, that's when you accelerate your chain fatigue failure rate and can lead to ultimate failure if not caught in time. Go back to Cody on our guide design.
All right, chain guides, they come in a multitude of shapes, sizes, and materials. Stamped, cast, or reinforced nylon bracketry is used to typically mount a nylon chain contact surface. I believe Jason touched on the nylon material used a little earlier on the tensioner slide. The nylon bracketry that we use, they uses the same PA66 nylon that the contact surfaces use, but they'll have like a 30 to 50% glass fiber reinforcement, which makes the guides very durable. Chain contact materials are designed to resist wear and provide a low resistance surface for the chain, and are designed to last the life of the system. So Jason is going to dive into that in a little bit here in a second. The guide should last the life of a timing system. Damage to a chain guide is typically the result of another issue in the system, such as instability, a lack of lubrication, or a tensioning or variable valve timing system issue causing instability. Now, like I said, Jason is going to dive into the technologies and what you typically can see out of wear.
This is how guides typically wear or are failed. Guides just like tension is usually, like Cody was saying, usually lasts the fatigue lasts of the system where the engine is running normal and you have good oil quality. Maintenance is key to this equation. Guides show wear in several ways. So if you look all the way to the right, you'll see an image with pretty typical normal wear patterns. It's not gouged, it's not grooved, it's not melted. You just kind of see a pattern where the chain links were riding against the surface. The nylon does a great job resisting this wear. And the reason why I use PA66 is for those wear properties. When you add the glass fiber reinforcement, it gives it structural integrity, but it makes it very brittle for the wear surface. It would aggressively wear out. This is the reason why you don't use glass fiber in contact components, and you do use glass fiber in structural components, because it makes the part much stronger when it comes to applying loads when you add that glass fiber. So moving left, you'll see aggressive wear on nylon, but still functional. And then all the way to seeing some nylon that's grooved and pretty heavily damaged from a chain that had met its fatigue life and was going into ultimate failure, and those links are starting to break and groove into the nylon. All the way to the left, moving to absolutely failed broken guide. That is one guide. That 1, 2, 3, 4 images to the left, that kind of L shape of images, they're all to the left and hooks around a little bit. That was one guide that went through system fatigue and finally got to the point where the tensioner system could not maintain stability to the point of actually breaking this guide. But leading up to this, you can see long term of what was going on. Lack of oil condition. This chain was actually moving some of the nylon material, kind of melting that surface. So this was kind of a long-term failure, all leading all the way up to an ultimate failure, and finally just breaking the tensioner guide because the tensioner could no longer stabilize the system, and you had chain whip and the components began to break. A chain that has met fatigue life and begun to ultimately fail will degrade guides by digging grooves and deduce or broken links, just like I was talking about and pointing out in the images. This chain whipping thing is a consistent theme as we're going through all these components. It is the main contributor to system failure. I'll take this all the way into, I kind of already described it in the imagery, so I'll take this all the way into that melting factor. So lack of oil can be due to clogged small port oiler, a small port oiler, or low oil pressure, or a sludged engine, typically from poor maintenance. Guides can also fail to the same thing the same theme we've been talking to, and that is either misfire or VVT system malfunction. Anytime you have lack of oil pressure, a sludged engine, or some type of malfunction inducing or producing harmonics or shock loads to the system, you have then accelerated your fatigue cycle. You've decreased your fatigue life, and that fatigue failure will lead to ultimate failure. We're very excited to talk about our new product. We entered the VVT Sprocket market with the 454, which you guys are very familiar with this application, and there's many options out there in the market. We didn't just go buy an existing component and put it in a box. We reverse engineered and went through development on this component, and truly has something unique in the market from OE and from other aftermarket options. The main point is our unit delivers 10% more torque, that is stator to rotor torque, with 20% less drag at the same oil pressure. So our unit just responds quicker and moves easier with the same oil pressure. We did this with a tight tolerance, long duration rotor vane tip design, which creates a frictionless function. There's no contact between the rotor vane tips and the stator, but it's extremely tight tolerance, so we've controlled no cross flow from one side of the cavity to the other side of the cavity, so we maintain variable valve timing function. That's where the quick response time comes from. The result is a better replacement part for repairable high mileage engines. Those are engines that may have some head wear but are still in spec. It's also a great option for remanufactured engines, extending the life of the engine as a whole. A little more detail on this design. You guys are familiar, this industry is familiar with these designs. So just speaking to it, reduced oil flow to the VVT phases is a common trait of this engine and result in poor engine performance. It'll throw codes, it'll have audible rattle. Everybody knows about the issues with the 5.4 in the industry. But a lot of these engines are repairable. The front journals are not beyond spec, and you can repair a lot of these engines with a simple VVT replacement or VVT and timing set replacement. This frictionless concept also eliminates another fail point. Without having that contact rotor to stator and having that frictionless design, you don't have to worry about that wearing out. The OE unit had a vane blades and were loaded with a leaf spring behind them, so they would wear over time. Other components in the aftermarket use like a nylon seal, like a wiper blade, and that will wear over time. So this is a very unique design, and it produces a better performing unit. I can't stress this enough. Same oil pressure, you get more torque out of the unit. You get a quicker reaction time, and it's got less internal drag. So it just performs better. And we've had this both in testing on VVT fixtures, and we have this in real world applications as well.
So on complete system, to all the points we just discussed, when you're servicing the timing system, it's highly recommended by us to replace all the system components. Even if you know what your issue is, you properly diagnose a specific system issue, that system issue would have already stressed or wore or damaged the other system components. For example, and we probably went over this, a fatigue chain, can work a tensioner past its operational range. Once that tensioner is past its operational range, it's going to result in chain instability in the system. Chain instability in the system results in chain guide damage, and sprocket tooth wear and possible tensioner damage as well. So it's kind of like a domino effect. When you got one thing going on in the system, replace all the system components. For those reasons, and the fact that timing component cost is a fraction of the labor cost required to replace the components, it's definitely recommended to replace all the components. And in the engine rebuilding world, a fresh start with all new components is going to maximize timing system life and reduce, chances of returns or comebacks. When and how to replace timing systems. Sure, everybody listening knows, remembers timing belt intervals that were, popular in the 90s and early 2000s and even still today. Those were recommended by the manufacturers and they were easily found. Of course, you wanted to follow those strictly as well. But with all that said, you're not going to find those recommendations for timing chain systems. Chain systems are generally considered by the manufacturers internal engine components. So they're not given replacement intervals. They're kind of considered a lifetime, type item. But with that said, the way engines last anymore, you're expecting 250, 300,000 miles out of an engine in some cases. You're typically going to need to install a timing chain system in that engine to make it that far. So Jason touched on this earlier. Typically, an audible noise detected from outside the engine, or hopefully a check engine light to give you a little bit of warning due to improper camshaft to crankshaft correlation, or just that was a fancy way of saying the timing is not correct. So those are some common symptoms of timing system fatigue. And then how to time an engine. I can't answer that today on this presentation because it would be a long presentation. There's no universal way to do it. Every engine has a specific and often complex procedure to set the engine timing. Special tools may be required to hold the shafts in proper locations during the procedure. Some applications require aligning marks to static locations on an engine block or head. Some applications align sprocket marks to other sprocket marks. And then what's really common in your newer, applications is aligning marked chain links to sprocket timing marks. So the main takeaway here is just do your research when working on an application that you're not familiar with. The information's out there. Diagrams can be found through major tech sources. Cloyes has detailed tech videos for popular applications I'll touch on a little bit later. And if you can't find anything, we've got a tech support line where Josh Mafus or myself, we're always willing to help. So feel free to give us a call at any time. Something Jason just touched on is the introduction of camshaft phasers this year for us. We've been busy in the product development department the last couple of years getting these ready. We first started with the launch of the modular 5.4 and 4.6 3-valve engines with the camshaft phaser. With these components, we built complete timing system kits for that modular Ford, and our latest development was the GM Ecotech 4-cylinder engines. These kits are going to include all the timing system components along with the VVT phasers, the torque to yield bolts for those phasers, because you should not reuse phaser bolts. They're mostly all torque to yield. And in the case of the Ecotech kits, we include the solenoids as well. These kits are beneficial because you're saving money over buying individual components, and then you're getting a complete high-quality system from a trusted supplier. And another thing to touch on, next year or early next year, we actually plan on launching the GM high-feature V6 components as well. It's going to be 3 separate phasers that cover all 4 phasers that are on the engine. We'll also have the solenoid for that application. There's 4 solenoids, but it is the same part number for all 4. Another new product launch that we've launched this year is a water pump kit. We launched the water pump kit for the Ecotech application. The Ecotech system was the obvious first kit for us for water pumps because of both the volume and the integration with the timing system. The water pump kits we do introduce are going to typically be for timing chain driven water pumps. The Ecotech pump is driven by the balance shaft chain. So when you're replacing the timing system, you might as well replace the pump wire there. We do have plans to expand our offerings. Like I just said, the Nissan 3.5 and 4-liter V6 engines is going to be the next pump kit to launch. That's also a chain-driven pump. And then hopefully by late next year, we'll have the Ford Duratec 3.5, 3.7 engine pump available as well. During the development of these pumps, we test both the OE and the aftermarket samples together or separately to the same defined parameters to ensure proper function. Another product line we're proud of is our belt kits. This is not a new product line for us. We've had these things for a long time. We offer more than 110 timing belt kits for the North American market and have a 95+% coverage according to Epicor catalog coverage analysis. Our kits include premium OE quality belts, and tensioners and idlers that meet our strict quality standards. And we're going to jump back to Jason for some product development information.
Yeah, so our approach on product development is, of course, to innovate, optimize, validate, execute. These images here are showing some of our test fixtures. We actually designed an in-house test tensioner tester. We use engine components as test fixtures. We've got 98 years of engineering and manufacturing experience to back this process of reverse engineering. And we back our products with a limited lifetime warranty. Component verification. This is to the left showing that tensioner tester a little bit, where we're doing flow inspection, oil jet functionality, mounting surface qualification, check valve operation, pressure calculation, flow calculations. To the right, we're using a 5.4 head or Ecotech head actuating solenoids, capturing a VVT phaser cycle time, flow inspection, checking oil pressure at a local oil pressure at the VVT, as well as charging the system hydraulically, so we know our input-output pressure. We also buy from the industry, buy core engines. We like to see engines that are damaged, broken, particularly if it's timing related. We like to see what's breaking and if there is anything that we can solve. So we take these core engines, then we rebuild them to a good enough status so that we can use them as test fixtures. We hydraulically charge the entire engines. We install, we rotate. We do hydraulic flow calculation. Every component that we develop for a system, we also go through full system analysis. And to enhance this process, this year we're adding dynamic testing with a motoring rig. This will give us the ability to actually program RPM ranges, pulse width modulation with for VVT systems. We're actually going to induce harmonics by blocking out compression, using compression signals to create vibrations for some fatigue testing. So we're really excited about this enhancement. As you know, we manufacture components. We have to have suppliers as well across our product types. This is just to show that we have a qualified global supply base. All of our suppliers are certified. Cloyes invest in our own tooling with our global sourcing partners. We do on-site supplier qualification. We have process control. We require suppliers to provide production check sheets and production data along with their certifications. So this is an oldie but a goodie. Most in this industry have seen this from us, the 3019 LMS. It's the GM 2.2 tensioner elimination kit. It's a simple concept. The tensioner was a common fail point just due to lack of oil getting to it. There's a little cup plug with a small diameter oil plug that loves to get clogged up and cook the tensioner. We were able to, GM designed this block to be a standard spin resistance, so they had BorgWarner actually make this chain special, elongated to fit the tensioner in. We just simply designed a chain that made a tight three-piece set like we do for high performance. But due to concerns about being four-cylinder and the chain fatigue life, we wanted to go ahead and test it. We always do some type of testing, real-world testing or testing before we launch. We actually tested this with Cody's favorite, dirt track front-wheel drive application. And these guys were running 7,200 RPMs with these little 2.2s. I had one customer that, the racer we were sponsoring, he was replacing a tensioner every 2 races. He went 2 seasons on this timing set. This has been a real success for us. We have 2 versions of it. We have the standard MS, and then we have the MS using an OE chain as well for the engine rebuilders. Now we'll go into the technical information. Cody will take it from here.
Yeah, something we wanted to bring attention to is our new website. We launched a new website earlier this year. It's a great source of information. It's got a great part finder where you can look up the application, and it'll give you the specific components or timing kit for your engine. It gives us details on products. The tech center on the website is also a great source of information. It's where you can find all of our installation tips and installation instructions. It also has a link to all of our tech videos that I'll move on to now. Our tech videos, like we mentioned earlier, we got like 2.5 million views on YouTube since we launched them in 2013. I believe we got a dozen different application, full installation videos. And then we've got a couple, other general, high performance or just general tech data type videos. But these videos are great sources of information. If there's anything involving the installation, as far as information we want to get to the installer, we include it in there. If there's special, tools required to install a timing system, we show those tools. If a tool is recommended by a manufacturer but not required to install, our timing components, we're going to show you how to install it without those special tools. To try to save the end user, a little bit of money if they're the ones installing the set. So, like I said, these are great sources of information. Along with these videos, if you got any questions, I mentioned our tech line earlier. That's also another good source of information from us. So that completes our presentation. We sure appreciate everybody listening in, and we're going to turn it back to Joe for question and answer session. Thank you, guys.
All I can say is wow. There's a whole lot more going on than I ever imagined. I'm sure that most everybody has been faced with a lot of these changes. Okay, we've had some questions. Let's get started. First question, Andreas Gomez. How do you test VVT? Which oil pressure values are used? Oil recommendations such as cleaning, oil filter replacement? So it's just a multi-part question. How do you test the VVT? Which oil pressure values are you using? And what oils do you recommend for such as for cleaning and oil filter replacement?
So the testing is. You hear me?
Yes, go ahead.
Okay, got the music in the background. All right. So testing is multifaceted. We're doing testing here in this facility in Fort Smith to validate test results with our supplier. From our supplier, we're getting full test results. How many parameters, Cody? 6, 7 parameters. So it's giving response time, torque produced, torque required, drag. Help me out, Cody. There's something else I'm missing here. Oh, lockout pressure. Leakage. So we got all these test parameters, and all production units are 100% tested across certain test parameters. So nothing is going out the door that's not been tested. Then what we do is here at our facility, we validate what we're getting and test results from our supplier. And again, we visit our supplier, we validate the process with our supplier, we have process control with our supplier, but then when we get these units in at production during the quality receiving inspection, we then destroy a certain number just doing our own hydraulic testing to validate what the factory test results are. So that covers that question with the testing. The other question on oil to clean the units, I guess I'm not 100% clear there.
I'm sorry, I missed that. What was your question there, Jason? You didn't catch which?
He's asking what oil quality to use for cleaning the units. I guess I'm not 100% clear there. Is that for reusing a unit or something of that nature?
I'm not sure. Let's see. Andreas, can
Okay.
you clarify that if you would, please? He does go on to say, in a functional engine test, which RPM and type of oil are you using?
Okay, so that's multifaceted as well. Here at the DC, we're using 5W20. The supplier is using a different specification. Oh, it's right on that line though. In our test vehicle, real world test vehicle, that engine had been moved to diesel oil 15W40 because of the VVT failure of the past. But once we did the repair, it was moved back to 5W20. As far as filters, we just recommend good quality filters with a check valve and good maintenance regimen. If you're using full synthetics, do intervals where you're keeping your system clean. And one of the questions that I missed there was the pressures that we're testing at. So here at the facility, we're testing in operating pressures, from 20 through 60 psi. The same thing with the supplier. We're testing at 3 different pressures, all within engine operating range.
Titanic, are the tensioners located on the drive side of the chain or the non-drive side?
The non-drive side. So you have a torque side and a slack side. You have the side of the chain that is being loaded to drive the camshaft, and then the other side, the slack side, you have the tensioner on the slack side.
Jose Delgado from Vega in Mexico. When you are going to install the tensioner, is it recommended to put some sealant or not?
No. Hard no. So we see this over and over again with products that are returned to go under analysis. These tensioners are machined to be perfectly flat and to mate to a perfectly flat machine surface on the head. When you introduce sealant, you very quickly introduce the possibility of sealant getting into the oil port inlet of the tensioner, and it's over. The smallest amount of silicone blocks the entire passageway going through the check valve.
Pretty adamant about that, aren't you?
A little bit.
Okay. From John Gurning. Due to the expense of cam phasers, should they always be replaced as part of the timing chain system? Is there a way to determine if the cam phasers can be reused?
It's a great question. Generally speaking, we're seeing phaser failure before timing system failure. So usually the question is the other way around. Should you go ahead and replace the entire timing system when you're doing phaser repair, especially with the Ford 5.4, because there is a method to replace just phasers without pulling the timing cover and just reusing the timing components. You know your phasers, or to answer his question, if it did happen to be that way, to Cody's point earlier, the amount of labor required to go deep enough to replace all timing components, it's a shame not to go ahead and do VVT units while you're there. The way we're bundling this as a kit, it's a much more affordable way to do it as well. I'll add that to it. But even if you have VVT units that are working, no rattle, no check engine light, you just need to replace the timing components. For example, like on a high feature V6, you may get by with that. The first cycle for a time period, you're not likely to make it all the way through that timing system's fatigue lap before you're going to run into some type of VVT functional issue, whether it's solenoids or VVTs. Anything to add, Cody?
Oh, pretty well covered it.
Next question from Glenn Katanik again. How does the Cloyes VVT design work with oil that has not been changed on a regular basis? A lack of maintenance.
That's a really simple answer. You can have an engine with a lack of maintenance, poor oil quality. If you're suspect of that situation, our tech video covers how to pull the camshafts, pull the main caps, and check the front journal tolerance. If you're outside of tolerance, you're running the risk of not being able to repair with just timing and VVT replacement because it will hemorrhage at that front journal and not feed the VVT sprocket. If you have an engine that hasn't been maintained, that great, but you pull the camshaft, measure those front journals, they're on the top side of tolerance, but they're still in tolerance, then you're most likely going to have a successful repair to put the fresh timing set on and VVT sprockets, and everything's going to work.
Okay. Jose Delgado, what is the guaranteed lifetime of the VVT cam phasers, for example, on the Ford 5.4?
We did a 500-hour durability test on these components that all checked out at the end of the 500-hour test as far as wear between components and functionality, and still had reaction time, it was still in spec in all test parameters and looking at the worn areas of the VVT units.
Okay. Jimmy Stray says, thank you, great seminar. And from several people, I am getting word that yes, they could hear my audio on the introduction, but they couldn't see the sponsor stuff. So I'll have to check into what is going on with that. This is not the first time that's happened. Ed Anthony is asking, are there job openings in your U.S. facilities at this time? First time we've had
time to reach out to us to my email address.
There you go, Andres. Okay, Ed Anthony, there you go. Andreas Gomez, do we do a functional test at the end of our assembly line? What is the oil they recommend? Use 5W30 or 5W20? If they do a functional test at the end of the assembly line, what is the oil you recommend?
5W20 is going to capture everything between Honda and Ford, and 5W30 captures about everybody else, like GM. I don't think you're going to have any issue using 5W20 as a test oil with a fresh remanufactured engine. That go a little thinner than thicker on the test. I think you're going to have a better functionality baseline. And
he says that's mostly for the Ford 3 valves that he's questioning, so that should cover that.
Absolutely, 520 on the Ford 3 valve.
And thank you, Mike Osterhaus, for clarifying what was going on with my video or my introduction. Andres also asking regarding oil, how often does it need to be replaced due to dirt, oil, and dirt in the oil filter may cause VVT failures? Question. Will dirt in an oil filter cause VVT failures?
I think we need to maybe cover, once you do this repair. So even if you do a simple VVT sprocket replacement, which you really don't drop any debris, you're just pulling valve covers and doing the replacement. No matter what your repair is, drop the oil out of the oil, drain the oil out of the oil pan to make sure all debris is removed. Start with a fresh oil filter. I think beyond that, there's not much you can do. If you have a heavily sludged engine, you're already kind of running a risk. But if you don't have a heavily sludged engine, just an engine that's, oil stains, but everything's, still functional, then you just need to start fresh.
Okay, Ed Anthony is asking, how long do phasers generally last with proper maintenance of oil change?
We're seeing anything from 80 to 140. The test vehicle that we used was already in VVT failure at 140 and had been for some time. It was a really good example as a test vehicle because it's been maintained okay, not exceptional, but not poorly. And it had VVT failure, but we had healthy heads. And so we were able to do 2 rounds of VVT testing, and the second round including the full timing system. So got to see it at 140 and saw that VVT sprocket replacement repaired the engine. And then at 160, 165, did a full system repair, and that thing's up to around 15,000 miles now, I think, and as our real world test vehicle, as one of our test vehicles.
Very good. Ed Anthony obviously is a vocational instructor, and he says it's his students who are inquiring on the job openings. Very good, guys. Glad to see that you're want to stay in the industry. All right. Any more questions? All right. Looks like that's about it, guys.